Welcome to the Industrial Problem Seminar. It's a great pleasure to introduce Dr. Michelle Snider. She is a senior data analyst on the solutions team at Service Robotics and Technology, which is SRT Labs. She spent 10 years as research staff member at the IDA Center for Computing Sciences, a federally funded non-for-profit research center working to solve the NSA's hardest problems. Dr. Snider holds a BA in physics and a BA in math from Smith College and a PhD in algebraic combinatorics from Cornell University. She currently serves as the chair of the Policy and Advocacy Committee and Executive Committee member at large for the Association for Women in Mathematics. She's going to talk about squishy mathematical reasoning in a robotics startup.
All right. Thank you, and thank you to the IMA for hosting me today. So I'm going to talk about squishy mathematical reasoning in a robotics startup. So the outline of my talk, as one might guess, I'll go through a little bit about my background, how I ended up here, and then talk a little bit about what Service Robotics and Technologies does as a company. And then I'll give you an example of some of the kinds of mathematical or mathematical adjacent analysis that I've done for SRT Labs. So, of course, when I was invited to give this talk, my first thought was, of course, I'm not qualified for this, right? I can't get up in front of people and tell them that I know what I'm doing as a career mathematician. I've known what I was doing the whole time. And I remembered as a graduate student, when I was starting to think about leaving academia, I had read a lot of books and watched a lot of talks about people's career paths. And they, even if they weren't exactly linear, they certainly seemed intentional. And I had always wondered, how did people end up where they were? How did they even know such and such a job existed? How much of where they ended up was luck versus preparation versus research, and so on. And so this talk is a little bit of my attempt to give one that my younger self would have wanted, and to remind me that, yeah, it's easy to put a narrative on your choices when you look back with hindsight, but that doesn't mean that everyone really knows what they're doing in the moment, or what they're doing next, even if they say they do. So just a little bit about my background. I went to Smith College. I majored in math and physics. And of course, Smith is a women's college and a liberal arts school in Western Massachusetts. And while I was there, I did several REU summer programs in physics, where I quickly learned that I didn't like being tied to a lab. I really liked doing math in coffee shops, and that's why I decided to go to graduate school in math instead of in physics. But at the time, I kind of wanted to be a professor at a small liberal arts school like Smith. And a PhD was a prerequisite for that. So I really went because I had this idea about what I wanted to do, I guess, when I grew up. And I figured, I'm good at school. They're going to pay me to keep going to school. So I'll do that for a while, and we'll see how it goes. So I went to the University of California in San Diego. One of my key factors in deciding that was I was done with winter. And so I decided to go someplace warm and sunny year round. I had a little bit of catching up to do due to my liberal arts background, but I managed to pass all my qualifying exams. And then I started looking around for an advisor. Again, I didn't go in with a plan about what I wanted to do my thesis in, just kind of taking it one step at a time. So I talked to people in a bunch of different areas, including math education, numerical analysis, combinatorics, and in every meeting I had, I felt like they just talked at me for an hour about all the work that they did. Then one day I was riding the shuttle back to graduate housing, chatting with another math graduate student, and he said, there's this new professor who's looking for students. No one really knows who he is because he just got here, so you should maybe go talk to him. So I did, and it was the first meeting that really felt like a conversation and not a lecture. And I was really excited that within the first meeting, he was able to start sketching out a problem, which I could understand and start thinking about. So this is one of the cool things that I like about combinatorics, is that the questions are easy to understand, even if the answers are hard. Whereas some of other types of mathematics, I felt like even understanding the open questions would take years. So at least in combinatorics, I could understand the questions. It's a good start. So for those who aren't familiar, combinatorics just means counting problems. So if I have 5 pairs of pants and 6 shirts, how many outfits can I make, right? So the best response I've gotten to that question was someone who was not a mathematician who thought about that for a second and then said, isn't that pretty well understood? So yes, the pants and shirts question is indeed well understood. But obviously you can then count more complicated things. So in algebraic combinatorics, you're looking at problems that are kind of at the intersection of algebra and geometry and topology. And then you can map those into counting problems. And then you can try to solve them in these more simpler spaces, more concrete spaces, and then map them back to these more abstract algebraic spaces. So you essentially can describe spaces by putting equations and conditions on them, and then map those to mathematical objects. And in my thesis, those objects were juggling patterns. And yes, the juggling patterns that you first think of, like a person with balls throwing them in the air, they just have mathematical rules, right? They have to move forwards in time, we've decided. You can't throw 2 balls at one time, 2 balls can't land at the same time. So with these mathematical limits, you can then describe the space of juggling patterns and then apply those to various different kinds of, you'd be able to map those back to these algebraic spaces. So again, it's just about taking complicated problems, mapping them to simpler spaces, and then mapping them back. So somewhere in the middle there, my advisor moved from UC San Diego to Cornell University. So I found myself right back in the middle of winter that I had tried so hard to avoid. But it was actually a great experience. And so I got my degree at Cornell. So over the course of grad school, right, I learned more and more about all the different pieces that go into being faculty. And I'm also looking around, seeing that schools are hiring, maybe fewer tenure track positions than they used to, more adjunct positions. And having already experienced being uprooted one time for my job across the country, or for math, I was ready to look at other options that didn't involve doing multiple postdocs in pursuit of a faculty position. So started thinking about looking around, what could I find that I could do outside of this? So the tricky thing is that I had spent all of these years getting deeper and deeper into the weeds of this little corner of mathematics, right? That's what a thesis is a very, very specialized problem. So I had done some programming in MATLAB for my thesis, but I still kind of felt like I didn't really have skills necessarily that would be applicable outside of this little area of algebraic combinatorics. So I started just applying for everything I could even think of. I even tried going to the Cornell career office and have them help me with my resume, and they just didn't really know what to do with me either. So that was not reassuring. So I found this book. So what are you going to do with that? Finding Careers Outside of Academia. It's in its 3rd edition, which I think speaks to its lasting power, that this is something that a lot of people are interested in. But if nothing else, this book gave me a lot of examples of people who had found other options. My favorite one being that Tom Magnazoi, who got a PhD in chemical engineering, while he was working as a mechanic in the garage he owned with his brother Ray. He taught in chemical engineering for 5 years, then quit teaching to go back to the garage. And you may have heard of him as Click and Clack of the NPR show Car Talk. So just because you're on an academic track doesn't mean you can't end up, hosting the longest running show on NPR. So it's kind of a fun story out of that one. But I just kept applying for any job that I could find and saying, wow, I really just wish someone would hire me because I'm smart and I'm good at learning things, not because I, am proficient in a particular software package. So I was complaining about this to my father, and he saw this ad in the IEEE Spectrum, which said, well, it was written for electrical engineers. So it's full of words that I did not understand because I was not the target audience, but he had highlighted these 2 sentences for me. And it said, we hire primarily math and computer science PhDs. And since the nature of the job is constantly changing, we hire based on strength of background rather than specific expertise. So I thought, wow, that sounds like exactly what I want, but I really don't understand what they do besides these two lines. So I sent an email to the contact on the ad, and I said, it wasn't even a cover letter. It just said, I'd like to find out more about what you do. I attached my resume, and then they wrote me back, inviting me down to Maryland for a full interview 2 weeks later. So at that interview, or before the interview, I tried to do the due diligence of research the company, and there was just very, very little information on the internet at the time on their website. I didn't really know any more than I had before that. So I show up for the interview and I find out what is now on their website, this paragraph, that IDA is a not-for-profit federally funded research center that is under an umbrella contract working for the NSA. So the idea is to take the harder problems, the longer term, sort of higher risk, higher reward projects for the NSA, and have a bunch of people work on those in this sort of halfway between government and academic type environment. And then the center sort of acts as a bridge between the two worlds. So because of security issues, I am just pasting up verbatim a paragraph about what is on the website, about the types of mathematics and the types of areas that people at the IDA centers work on. I will neither confirm nor deny that I have worked on any particular mathematical area over my 10 years as a research staff member. But I do just want to talk a little bit about how, so I was at the Center for Computing Sciences in Bowie, Maryland, but there's a sister center in La Jolla, California, and one in Princeton, New Jersey. And all three are filled with people who were hired because they're smart and good at learning things. Everyone I worked with was mathematicians, computer scientists, electrical engineers, physicists, and it's a very academic environment in the sense that it's very flat in terms of management style, very self-directed work. So very much like an academic job, except you never have to write grants and you never have to teach calculus. So if that is a plus for you, that's something to think about. And all three centers run these summer programs called SCAMPs, which are basically REUs for grown-ups, where they bring in people from academia, from industry, from other national labs, and do a 10-week focused research project. So the idea, again, is to take a diverse set of backgrounds and attack problems from new angles. So just a quick plug, wherever you are, graduate student all the way up through emeritus faculty, if you want to spend 10 weeks in your summer where all you have to do is think about an interesting problem, and you get a break every day at 3 o'clock for cookies, that's a fun thing to check out on the IDA website. So as I said, I am in Maryland, so I am right outside of DC. So while working at CCS, at some point around 2015, I saw an article in the AWM newsletter about their Capitol Hill days. And I thought, hey, that's something different. I've never thought about doing that before. I had only been involved with AWM a little bit while I was in graduate school. And I was looking for ways to stay connected to the non-classified community. And so these events they basically take groups of AWM members, and that includes students, faculty, people from industry, people from government, and send them into DC for a full day of meeting with legislative offices and advocating for funding for math and for STEM in general, for women and other minority groups in STEM. So it turns out this was my gateway into getting significantly more involved in the Association for Women in Mathematics. It didn't take long until I was suddenly running the Hill Days, and then I was running for executive committee. So just you gotta watch out once you start volunteering for things, people start understanding that you'll say yes. So but I did very much succeed in building out a network within the AWM of mathematicians working in all different kinds of jobs all across the country. So then along comes COVID, which obviously threw a monkey wrench into pretty much everyone's lives, I suspect. But working at a place where all of our work was classified made it a little bit more complicated, right? So they did send us all home for a couple months at the beginning of COVID, but by fall 2020 we were back in the office. So at some point in here, I was chatting with the previous coordinator of the Hill Days about how I was finding this a little bit stressful, and she said, "Why don't you consider coming to work for me at my all remote startup?" Right? So a startup that was remote before COVID, before it was cool. So as the Chief Operating Officer of Service Robotics Technologies, she saw a great opportunity for me, both with my mathematical, technical, but also presentation skills to be able to fit in on the solutions team, where I would be working with clients, but also doing math. So the stars seemed aligned. So I closed my eyes and jumped from my world of a stable government job into the world of tech startups. So all of this to say that I haven't really had a plan, just kind of rolling with it here. So this is how I ended up here as a senior data analyst for Service Robotics and Technologies. So first, I'm going to go through a little bit about what the company does to give you some context for the types of things that I work on. So as technology improves, I bet you see ads all the time for let's just make everything smart. Like let's tie everything together, right? You can get smart blinds in your house that go up and down depending on how much the sun is hitting them. You can get smart lights, you can get a smart thermostat and control it from your phone, even if you're not home, right? You can even have your fridge tell you if you're running low on eggs and milk while you're at the store, get text from the fridge. So all of these things, though, are probably made by a lot of different manufacturers, and they all come with their own apps. If you're going to try to control everything, they're not going to talk to each other. They're all going to have their own data. They're all going to have their own analytics. And maybe some of them are from the same company, but then you're kind of getting tied in the more you buy from one company. Anyone who owns any Apple products is probably familiar with this ecosystem problem where you're kind of locked in to one manufacturer. So everyone agrees that there should be standards for all of these different internet connected devices, but it's really hard, right? This is a problem that lots of different industries struggle with. There's so many groups involved, so many competing ideas and priorities. And while there do exist now efforts to standardize the technology going forwards, that is not going to go back in time and fix all of the existing systems that you might also want to connect. So this is where SRT Labs comes in. So what we do, the company started specifically with a focus on robotics. That's why there's robots in the name. And understanding the information from one system can be used to affect another system. So you have all of these smart devices, maybe a bunch of control software with these application program interfaces that lets you get data out of them, and then data coming from all these different sensors. And what we do is we connect them all together into one central platform, which acts as a mission control center. So once you have this central hub for all of this data, you can do all different fun things with that data. So you can monitor all of the systems across, a house or a building or a city in one central platform, and then you can do analytics on that data. You can also allow one system to inform another one's behavior. So at the bottom here, we have this cleaning robot. It's like the size of a shopping cart, and you can program it to clean a hallway. But you could also tie that into occupancy and say, well, I want the robot to run after 100 people have walked through the hallway. Or maybe it's tied into the weather system and it says, if it's raining, I need you to clean the hallway after 25 people. And then additionally, you can get alerts. So in this messages phone symbol here, you can have any of these sensors whenever a particular set of conditions happens, you can get notified. So really, here's kind of the key points about what the company does, right? So our platform is hardware and software agnostic. So what we do is we plug into all those different systems and pull all the data into one place, right? So you can then buy, if you want this air quality sensor from one company, but you really like the smart thermostat from another, but you still want them to be tied together, we can pull them all into a central location, right? And then we can also add sensors to legacy systems to be able to monitor them, even if they weren't smart to begin with. So once you have all that data in one big ecosystem, you can then start to do intelligent analytics on them by looking at data from across different systems. That gives you a better understanding of the system as a whole, right? Whether that, again, is your house or a building or an entire city. So once you have all that data in one place, you can then enable either automation or robotic solutions. So you can say, if you see that the air quality reading is getting bad in your house, you can then trigger the air to turn on and clean out the system, right? Or you can have a cleaning robot turned on, as we talked about before. So as an example of the types of things that we could do in a commercial example, you think about like a supermarket. Like there's just a lot going on in a supermarket, right? So here, starting at the top right, you have a cooler and a freezer. So you probably want to be monitoring the temperature on those, but you also have systems that are keeping them cool, right? And so you maybe want to have a current meter, vibration meter on like your pumps and your compressors. You want to get a heads up if one of those is going to go bad before it goes bad and you lose the contents of the freezer, especially when you're talking about food. Then you have maybe a smart forklift back in your stocks and receiving area. You could have occupancy sensors throughout the store to monitor traffic. That could be just to understand how traffic flows. Could also be from a security standpoint where you have one in the cash office and you want to know if someone's in there when they shouldn't be, right? You also put a couple cleaning robots in here, which again, you could have running around, keeping your store shiny and spotless. Put some temperature sensors over there on your hot bar for food safety. And then up in the top left, you got your bathrooms. You could put in a smart toilet paper dispenser, smart soap dispenser, smart trash cans. So they'll tell you when things need to be checked on, tell the maintenance staff when they have tasks to do before people go and complain about them. So this is just an example of the type of thing where you try to figure out what things are that you want to address. And then we figure out what sensors you can put in place to help you monitor those things. And it doesn't matter if they're all from different companies. It's sort of the key. All right, so talk a little bit about some of the government projects. So we work in the commercial space, in the academic space, and also some in the government, benefiting from these small business innovation research grants. So if you just think about how much government infrastructure there is in this country, right? There's just a lot of it. And there's a organization called Nexus Labs. They did a survey and found that 87% of commercial buildings have no digital systems in place, right? And that's across the whole country. So one could imagine that that's going to be an even higher percentage with no digital systems if you look at government systems, right? So the way the government works, right, is you have these long-term investments in people, in knowledge and resources, and they're looking for incremental growth, right? In the commercial world, people kind of tear things down and start over all the time, right? Build brand new smart buildings where everything is as fancy as it can be. But in the government, we're really anchoring to the reduce, reuse, recycle model, right? So how can you just build on and improve what you already have, right? So there's an adorable Disney movie, which I will recommend if you haven't seen it, called Zootopia, where all of the characters are different animals, right? So you have the main characters, I think, are a fox and a rabbit. But at some point they go to the DMV and all of the DMV workers are sloths, right? So the joke there is that everything in the government moves very slowly and everyone knows that, even the kids get these zingers against how slowly everything works in the government, right? So the government isn't going to tear everything down, rebuild it, have some smart buildings and digital twins, right? But what we can do is go in and help them to modernize their existing infrastructure and to add IoT sensors to monitor anything from the vibration on a motor, on a 100-year-old lathe that is specialized to work on certain parts of submarines that just isn't going to be replaceable, right? We can monitor these things that they already have and not have them have to replace everything. So one example of something that we worked on, so this is called a paint booth. It's called a booth, but it's really big enough to drive a tank into, as you can see by this tiny person that I've put on the side of the picture. So what you have inside is there's pressurized lines for paint guns. You have a very sophisticated airflow system to pump air in from the top and have it go out the sides through filters that are designed to remove a lot of that, the paint particles that would then get in the air from the system. And then you have obviously people working in here, so you care about air quality and temperature and these sorts of things. So what we can do is we can go in and put sensors on all of these things, right? We can track the pressure in the paint guns, we can track airflow, we can track the pressure across those air filters to see how clogged they're getting. We monitor the motors, we can monitor temperature and air quality, and then we can also put in detectors for motion and objects in order to tell you how the booth is being used. So again, we have these sensors that would send alerts, like if something is bad, if your air quality is now unsafe for people, we would send an alert. But we can also do another level here of analysis where you can say, how is the booth being used? So we combine the different metrics, looking at people, object detection, motion detection, whether or not the fans are running, whether or not the paint guns are going, and we can sort of bucket things into these time, like an analysis of how the booth is being used. If it's available, meaning it's empty. If it's preparing, meaning people and things are moving around, but no painting is happening, versus running where, full four bore, fans are on, paint guns are going. And what this gives is if an organization has a bunch of these across a base, then they can see how they're utilizing their space. They can see, really, we'd be better if we reorganize the way our workflow goes, because now we know exactly what's happening in our booths, right? Okay, that is the big picture of what SRT does. So now I'm going to move into a little bit about what it is that a mathematician does here. So when I was in graduate school, I took some applied math classes, and some of my classmates were actually graduate students in the engineering program. And I was struck because one day they said that their favorite thing about taking math classes is that when you get a math problem, everything you need to solve the problem is in the question, and nothing you don't need is in the question, right? So when you're reading a math question, if it says, this variable is an integer rather than a real number, you know that that's important, right? And if it doesn't say an operation's abelian, and that doesn't follow from something else in the question, then you can't assume that it is, right? And apparently in engineering classes, that's not the case. The professors would like throw in extraneous information, not include all the stuff they needed. So that's kind of what I feel like what I'm doing now is, I'm coming in with training from these very pure mathematical worlds where, again, everything is exactly, you can do a proof, you can do a claim, work out all of the edge cases and it's fine. And now I'm trying to tackle all these real world problems in what feels like a messy and uncertain space. So I will try to solve problems, and then I'm always trying to add like 1,000 caveats to the end to every result I get, because the mathematician in my brain is saying like, but we got to define everything here. And this is very much to the chagrin of our sales team, who's just like, right, but what is the answer that I can tell a client, right? Okay, so what am I actually doing here? I'm on the solutions team, which we joke is the problems team, because you can't have a solution if you don't have a problem, right? So what we're listening for when we talk to clients is to try to figure out what their problems are, what are their pain points, what is it that's making their days harder? And then on top of that, can we solve those problems with sensors and data? Because usually it's not, usually it's a policy problem. People don't usually need a ton more data so that they can think harder about their next step. What they really need is to have all the data that's coming at them anyway, synthesized into something that they can actually use that makes their day easier. And then we can start to think about how to improve things long term. So what we have to do is to synthesize everything from their daily process and then deliver it back into their daily workflow in a way that's non-disruptive. So again, it's very easy to like take a bunch of sensors, collect a ton of data, and then just hand the client a bunch of dashboards full of analytics that they just are never going to look at, right? So I can't just give them data. I have to give them what their next step should be. I need to explain it to them in a way that they can understand where it came from, but then they kind of need to stop caring where it came from because they just want to get on with their day, right? So one of the examples I think about with this is in universities, well, any any big air conditioning system, right? You have these air filters, and people used to have these filters in them that were like pretty cheap, right? So it wasn't a big deal. But since COVID hit, everybody realized that they need to put in these fancier filters. So these MERV 13 filters are much more expensive because they're able to filter out much smaller particles. So to make your building COVID safe, you have to buy these much more expensive filters. And so people maybe don't want to, they think more about how long is this filter good for? And maybe I don't want to throw it away on a specific schedule just because if it was actually going to last longer, because it's just too expensive to replace it more often than it's absolutely necessary. So what we can do is we can measure the differential pressure across a filter, which is a proxy measure for how much particulate matter has been caught in the filter, right? So the longer you use it, the more it gets clogged and the more that pressure goes up. But also the more that pressure goes up, the more energy you're going to have to expend running a fan to push air through that filter, because pushing air through the filter gets harder the more clogged it gets, right? So there's going to be this tipping point where you have used the filter, but you're not suddenly using too much energy to make up for not getting rid of the filter, right? So I can explain all of this to someone, but really all they want to know is, do I have to change the filter today, or can I wait until next month, right? So I want to be able to explain the process, but also just give them the answer that's going to help them move on with their day, right? And another piece about this adoption and being able to explain to people what we're doing is that there's a lot to be gained from this very straightforward automation of systems to make people's days easier. And we have to present it to them in a way that's respecting the expertise that they have and what they've been doing, things they've been doing for years manually, and we come in and we try to automate them. So there's an art to talking to maintenance staff about how what we want to come in and do is to help make their jobs easier, make their days better, not just replace them with an algorithm or a robot, right? We can't do something to their HVAC to make it save energy if they can't also then explain to someone who calls up with a complaint about how their room is 5 degrees too cold, what the system was actually doing. And we found that with some of these people who work in maintenance spaces, AI is kind of a dirty word, because that says, oh, that means you can't tell me why it's doing what it's doing.
So,
Is there a question?
Yeah, there is an online question. I don't know if you can see it in the question and answer box. I'll share it with everyone. So from meeting the client to delivering the solution, what is the best part, the most difficult part, and the easiest part?
Oh, that's a really hard question. I would say the most difficult part is always trying to figure out what is the actual problem that we can help solve, right? I mean, if you come in and ask people, so tell me about your job, right? They will tell you about their job, right? I talk to people at universities who start telling me about the parents that call in because their students complaining about the temperature in their room, right? And I'm like, well, I can't fix that, but it's sort of fun to hear, right? So I actually think that may be the best part and the most difficult part, because it's really interesting to hear about all the different parts of someone's job, and then try to sift it down. So I don't know if there is an easiest part, right? Again, we get a bunch of data and then we try to figure out what to do with it, but it usually just ends up bringing up more questions about what we could have done if we had different data, or what are the caveats that we have to put on this. I do also really enjoy the end when we actually get to tell people something useful out of all of their data. So I don't know that there is an easiest part. I'll have to think about that. Interesting. You guys have good questions. All right. So one of the things that we do, one of our products is called a space audit. And what we do is facilities managers, they know what's going on in their building. They probably have some kind of gut sense of what's happening, but they don't necessarily have the actual metrics, the actual data to be able to take it to their management to enact change, especially if that change requires an upfront cost, right? So what we can do is we can come in and we can assess whatever systems are in place. So either room reservation systems, occupancy data from smart lights, or maybe people badging into the building. And then we can layer in our own IoT occupancy sensors to monitor areas where we don't have other sources of data, And then we put this all together into a summary of how the space is being used, and then provide a kind of return on investment about what could be possible from either process changes or automations. So we've done these in a bunch of different kinds of buildings, including like big Fortune 100 companies, and also for a couple different universities. So I think given the audience, you probably have all spent a lot of time in university spaces. So I'm going to talk about some of the projects we've done there. So basically, every school is going to have some kind of system to track reservations, right? So looking at semester-long classes and individual. And then there's going to be some sort of building automation system, which will have, unoccupied or occupied settings, depending on when they expect people to be in the spaces. And this is really just a fancier version of the thermostat you have in your house, right? And I think for most of this, I'm probably just going to say air conditioner, because saying heating and cooling all the time is a little unnecessary. Then what happens is that a lot of universities have recognized that they could save energy by not just running their building in this occupied comfort zone all the time, but the kind of tailoring it to when events are actually happen. But again, these are two completely disjoint systems that don't have any way to talk to each other. So what a lot of them are doing is actually paying someone to sit there and enter reservation times into the building automation system, which just sounds like a terrible job, right? And their goal, of course, is to save energy. That's what we all want to do, right? They want to meet campus-wide climate goals, or they have pledges to achieve carbon neutrality, but they also care about making sure everyone's happy. And happy is measured by they just don't want people to call them up and complain all the time, right? Which I think we can all agree with. So when we look at these, we think about the way that spaces are used. So they'll give us floor plans and we'll kind of go through and break them down into these different kinds of cases. So red would be you have reservable rooms where we can look and say, this room is used on the times that it's in the schedule as being reserved. You can look at group study rooms or other kinds of drop-in spaces where there's no reservations, but people could come in at any time of day and use them. And so you might want to understand how much people are using them. We have purple for faculty offices, and we all know faculty work on the schedules that they want to work on. So that's not going to be a standard schedule. Green being limited in these limited use rooms, so administration, people that might be expected to be there from certain hours of the day on weekdays. And then of course we have the restrooms, and then the gray areas here are the hallways and things that we are not going to worry about here. Okay, so again, we're going to look at how people are using the spaces. So for reservable rooms, we looked at classroom schedules, and you can say, okay, this university is running their air conditioner from 6 a.m. to 11 p.m. every single day of the week, and then 8 a.m. to 4 p.m. on Saturday, Sunday. And they're doing that because it's easy to program. It minimizes the facility staff's time, and they don't have to consider these ramp up and cool down times. They just set it and forget it. And then you can see a classroom maybe is only scheduled 40 hours a week. But the trade-off that they've made, because they are trying to save energy, is that in the summer, they have set their building to 76 degrees, which I think is kind of at the upper range of what most people find comfortable. But that's their trade-off for running it for this many hours. So you could think about the different ways that you could affect this. You could say, well, maybe instead of running it all day, we would just turn it on only when there exactly are reservations. So on Monday, I'm going to start it at 8, and then at 10, I'm going to turn it off for 10 minutes. And then at 11:30, I'll turn it back on, and then I'm going to turn it off for 10 minutes, right? But of course, that might be infeasible depending on the temperature ranges. It takes a lot of programming to type all that in. So there's kind of an in-between option is one of the ones that I proposed. So what if you just turn it on right before the first class of the day, and then you turn it off right after the last class of the day? Then everything that's still in gray there is still going to be, it's now going to be time where you're not running it. And that's going to save them 50% of their time, right? So this is great. I'm like, hey, I just took 50% of the time that you were running this, you don't need it anymore, right? But to start throwing in all those caveats that I mentioned that gives my sales team heartburn, right? I say, I don't know what that means for your energy use. I'm just saying there's 50% of the hours. But I also know that I'm telling you to run it in the middle of the day when it's the hottest. That's going to use a lot more energy than the times I told you to turn it off. You would have used a lot less because it was already the cooler part of the day, right? So really what I'm showing them is just, here's the data that I measured, and here's what I can tell you about it. And then I would give even more detailed breakdowns if they wanted to know exactly, look over the whole week, how much of your time is in these like little tiny 10-minute breaks between classes, how much of your time is in these big blocks. If you say, well, it's only worth it to me to toggle the AC on and off if it's more than 5 hours, then you're going to be saving a lot more in that seminar room than you are in that classroom. Okay, so that's one way to measure things, is just what's in the reservations. But what if you layer in some occupancy sensors, right? So semester-long classes might be pretty reliable, but what about other types of reservations, right? If I'm going to start actually tuning the AC to only when people have reservations, I might care whether or not they're actually there, right? So this university was running their system from 6 a.m. to 6 p.m. And then in evenings and weekend hours, they were actually tailoring it. A person was typing in, here's where I want, here's the reservation. So only set the AC to being on when someone's actually there, right? So what we did is we put occupancy sensors in the rooms where they had reservations, and then started taking data to see, are people actually there? So what you see in this chart here is the light blue block in the left column represents a reservation. And on the right-hand side, that everywhere there's a dark blue line indicates that our motion sensor was triggered. So we decided to make an assumption that if someone shows up, we're going to count the room as occupied for an hour afterwards. So that's what the light blue blocks are on the side. So this is where we would recommend, if you wanted to tie it to occupancy, how you might make that change, right? So again, you start to see a bigger picture when you start to look across like entire weeks. And this university, they would have these people would make reservations for 2 days straight, right? So if you see here on the Friday, Saturday, Sunday, that's just a lot of time, right? And so if I'm the university, I say, well, if I'm going to run the AC for 2 days straight, I want to know if you guys are actually showing up, right? So then the university can make decisions about what kinds of policies they want to implement once they see what this data looks like, right? So if you're going to say, okay, if I'm only going to do this when there are reservations, what if someone doesn't show up? Should I turn it off again if no one showed up after 15 minutes? What about these people? There's a lot of times you see here where people are showing up and using the rooms, but they didn't actually have a reservation. So if you're going to say, I'm going to only tie the AC to reservations, are you just going to tell those people, well, you should have made a reservation, so just do that next time? Or do you also want to have a more complicated logic that does trigger the AC to come on once people have come into the room? And all of this is going to be a policy balance between what the university wants to spend money on and what complaints they're willing to put up with, basically. Okay, so all of that's great. You can do all this data and you can tell people, here's what we're seeing in your space. But the real question then is, so what? What are we actually going to be able to do with this? So this is where we come in and give recommendations for energy reduction opportunities, right? So can't really see the labels on this little chart here, but the idea is that everything that's in dark blue is something we collected data on. We have some classrooms, we took some representative faculty offices, some representative group study rooms, and then we extrapolated. So all of the gray bars represent what happens if we say, well, assuming that those were representative, here's your whole space, right? So this huge block in the middle here, you see are these offices. So we said, okay, well, we did a test on 2 faculty offices, but you have 20 faculty offices, so we'll just multiply those by 20 and say all of those were the same. And so this is where we kind of dig into these edge cases and we say, okay, well, this is what I saw in the data, but what does that actually mean for the university, right? And is it even representative? So we asked the university to give us 2 people whose offices we could put motion sensors in. Maybe they picked the 2 people who they knew were never in their offices in order to not have them complain about the fact that we had put occupancy sensors in their offices, right? So maybe you don't want to take action on saying, hey, faculty aren't in their offices 86% of the time, if that was actually not the best sample of the faculty offices, right? And so we can, again, give this sort of data and talk about, okay, I can tell you that 68% of the time across your whole building, nobody is in there of the time that you're heating and cooling it, but you have to decide what to do with it, right? And again, I have not said anything about how much energy or money, for that matter, they're going to be able to save, right? Because I am not an HVAC engineer. There are factors that go into how long it takes to cool down a room, how much you're going to let it drift, how much strain does it put on your system if you're kicking it on and off all the time. Where is that trade-off? I'm just showing them the usage of the space, right? I can say that will affect the cooling, but I can't tell you that that's what you're going to save. So the next question is, of course, but what if you could, right? It's all about what data you can get. So not every university has data at this granularity, but for ones that do, we can design experiments to test how much of a difference this is making, right? So here we have a university that has a fairly new building where every room already has an occupancy sensor that's tied into their heating and cooling system. So they have an occupied state and then an occupied standby state where they let the temperature drift a little bit more, but it's very easy to pull it back to an occupied. So maybe your occupied is like 72 degrees and then your occupied standby is like 74, 75. So it's very easy to cool it back down. And they're doing this already. And they have this data for every room, what state it was in for every 15-minute increment. And then they also have how much energy they're spending to pump air into those rooms via the fans. And then at the air handling unit level, which is feeding all of those individual room fans, they also have information about the temperature of the air they're pumping in and what it's coming back with. And that can tell you how much energy you're pumping into the building. So here we were looking at a fall timeframe, and so they were in heating mode. So you can think about how much heat are they adding to the building, which translates back to a cost. So what they wanted to know was, we're doing this already in this newer building, but maybe we want to do it in some of our older buildings where we have to go in and add occupancy sensors and integrate with the M1 to be able to control it. But we want to know if it's worth it. So what they did is they gave me a bunch of data when it was running, and then they turned it off for a week and said, how much of a difference did it make? So I kind of dug through the weather of the 2 time periods they gave me in order to try to find 2 24-hour periods where they actually had comparable temperature, right? Because doing a mathematical model of the temperature, the outdoor temperature, and how it affects their heating cooling is clearly well beyond the scope of a little project like this. It's just to figure out how much energy they're saving. So I picked 2 days that were comparable, and then I just added up all the energy that they were spending in the different and found the difference between these 2 days. So even just switching from from an occupied to occupied standby for about 18% of the time, they still were saving 12% of their energy on their room fans, which was in kilowatt hours, which directly translates to their energy bill. And then we also looked at the air handler energy, which again is like, we're looking at how much heat they're adding to the building. And so that is not going to directly be in their energy bill, but it's going to go back to how much they're going to have to spend in their boilers, how much they're going to have to spend pumping heat into the buildings. So it's not a direct cost, but it's going to also add into those savings. So we can do this kind of data or do this kind of analysis if people have this kind of data. And then finally, we do these sort of recommendations for cost savings. So we look for places where could you actually change the way you're scheduling classes to be more efficiently packed in either time or space? So here we had a building that had a whole bunch of different conference rooms and different floors and wings. And so you can look at this and say, wow, there's a lot of time in there where no one's using these. So what if you told people, okay, you have to schedule in 2A. If 2A is booked, then you can go to 2B. If 2B is booked, then you can go to 3A. And you can imagine squishing all of these into just a couple conference rooms, and then maybe you'd never have to do anything in the 4th and 5th floor, right? So that's a pretty valuable time saving or money savings, even for exactly the same amount of heating and cooling in 2 of the room or 4 of the rooms, if you could not run the other 4. And then my favorite suggestion, which obviously no one took me up on, was say that faculty data was correct. And if faculty are only in their offices 1/10 of the time, what if you assigned 10 faculty to each office and just made them share? And then you could turn off all the other offices and save so much money. But obviously that one didn't fly. But, you know, just another thought experiment about what you could do there. So finally, we'd say, okay, what do you, obviously you could automate by tying your room reservations or your occupancy to your HVAC. But once you have these sorts of integrations and once you have this occupancy as a baseline, you can look and say, well, what else is it that I can do with this? What other things can I automate? What other things can I trigger? So there's lots of things that could follow from this. But to be simplistic, if I have a floor plan and I can tell you where people have been throughout the day, I know which bathroom is going to need toilet paper first, right? So probably the people in the registrar's office, when they were making class schedules, were not thinking about how much toilet paper was going to be needed in the various bathrooms. But I have a PhD in math, so this is what I think about. Qualifications. So we're looking for all these places where you can think about what else you could do with this data, right? I've mentioned some of these before where you could trigger a smart robot to go on and clean. You could trigger work orders that said, hey, this many people have been through this part of the building, somebody needs to go check on the bathrooms. For that matter, you could start putting in these smart paper towel dispensers, smart soap dispensers, smart trash cans. So the maintenance teams can get notifications before things run out and people start complaining, but without having to check every single bathroom every day, right? So again, once we're laying this base layer and then we're adding different things on top. All right, so just to wrap up here, this is, I don't know if any of you have spent any time on these Creative Commons, no copyright reserved websites where you can just look for open source pictures, basically. And if you go in and you type in smart cities, you will see so many pictures like this that are just nonsensical. Feels like there should be some flying cars in there, you know, in amongst the binary numbers, but it also kind of feels like you're living in the world of Person of Interest, which is a TV show where it's just basically terrifying that there's data all around you all of the time. But this is not at all what I think of when I think of smart cities or smart buildings, right? It doesn't look like magical data flowing everywhere. It can look simple, like it's just cities putting in maybe smart water meters that can track the amount of water going into a neighborhood and how much water is coming out of that neighborhood, because that helps them identify leaks as soon as they happen and help the maintenance staff figure out exactly where to go to fix them as quickly as possible, right? It's looking like just tying heating and cooling costs to your, or reducing heating and cooling by tying your HVAC to your occupancy. It looks like reducing waste by not changing your air filters when you need to, you know, any sooner than you need to, just changing them when they need to be changed. It can look like making your existing infrastructure just last longer by adding machine monitoring capabilities, improving what you have rather than throwing it out and starting over. So you're, you know, reducing materials, having a more efficient allocation of your limited resources. So, you know, just basics, you know, saving the planet kind of stuff, right? So it's just, and you can get into the world of tech, it's really easy to stand there and say, all right, I think we should all be living in the Jetsons house. I want robots to be cleaning all of my windows and doing my laundry. But it's actually a really interesting problem to say, okay, where are people right now? Like, how can we meet them where they are and help them move towards a new way of thinking at a pace that they can work with? And that's a change management problem. And it's its own complex problem in its own right, right? And it benefits from a little bit of squishy mathematical reasoning, right? So, you know, we're not moving fast. We are really trying not to break anything, a little counter to a lot of the Silicon Valley startup sort of mantras. But that's okay. I think we're really trying to meet people where they are, move towards the future. But it does mean that sometimes it feels a little bit like you're talking to a sloth at the DMV. So with that, I would like to thank the IMA for hosting me, and I'm happy to take any questions.
Thank you very much, Michelle, for a great talk. People, you can just type your questions in the questions and answer box. I also put the message in the chat box that will be a Zoom meeting with Dr. Snider right after the talk. Yeah, so while people are typing, let me ask you, I'm curious, because if you look at what you're doing, so a lot of this is kind of being taught in some optimization courses and operation research programs. So in what way do you think that mathematicians have some advantage with, a broader background, but maybe not so much detailed preparation to work
Yeah,
with problems?
I think that the way mathematicians have an advantage is that we are used to, again, sort of taking problems and stripping them down to what is the most important thing, right? I mean, when you think about writing mathematical proofs, right, every line means something. There's nothing extra. You just everything is saying here's the steps that you're going through, and here's how you get to your conclusion. And so when we're coming into these spaces with these big amorphous problems where you have sort of haphazard data and people have lots of different pieces that they'll give you, well, what a mathematician does, we come in and we sort of take all those pieces and try to distill it down and say, what's actually important here? What are the pieces I can actually use to build a solution? And which ones are these sort of extraneous pieces of information that I can't do anything with or are actually distracting from the real problem? So it's that sort of analytical thinking, I think, that is really helpful for attacking these kinds of problems. Even if, I mean, there's certainly places where having a degree in optimization is going to be hugely valuable. But the types of problems that I'm working on, there's not enough data. There's not enough to build a big complex model on. So we're just trying to figure out what are the pieces that we have and what can we do with them.
And in terms of, the percentage of mathematicians in your group, is it sufficiently high? Or?
I'm sorry, can you repeat the question?
Oh, what is the percentage of mathematicians in your group?
Oh, in my group? So the solutions team is actually 3 math PhDs and 1 evolutionary biologist PhD. So we are actually really heavy on the math PhDs. And the CEO of the company has a PhD in space robotics. So we may not be a typical group.
Don't see a question. I guess people are waiting for the group meeting, but if anyone wants to raise a hand and ask a question, please do it as soon as possible. But one thing I'm curious about, I kind of noticed that people usually who study algebraic combinatorics are not so easy transitioning to industry. I don't know.
Yeah, no, I think that's true. I did not plan. I did not plan to leave. I didn't put anything in place ahead of time. So if people are thinking of transitioning, I would recommend that they definitely take some programming classes before they graduate, not after.
And maybe one of the reasons is, as you said, in algebraic combinatorics, you have very well-defined questions. And in industry, it's an art to ask the questions.
Yeah. Agreed. And I think that I have a little bit of an advantage because I did do my undergraduate in physics. And so I had at least seen some of the space outside of combinatorics. So it's kind of come full circle for me, but you're right. That is one of the great things about combinatorics is you kind of have these little boxes and you're like, I'm working in here. Yeah.
Yeah. Okay. Thank you very much. It was a really great talk. I really enjoyed it. Yeah, so you can join the Zoom link and also other people can join the Zoom link.
Okay, great. Thank you so much.
Sure, thanks.
Thank you.
Thanks.
Yes, if you click on the Zoom link, you'll just leave the meeting.
Yep, got it.